why do we introduce support and no singular value decomposition? Okay, why do we introduce SVD? The main goal is to do matrix approximation. Okay, so let's start from this part. If A is an n by n matrix with rank R, and the rank there is some other value k which is larger than 0 and smaller than R, we can use the singular value decomposition to find a matrix in the space of n by n of rank k that is closest to A with respect to the Frobenius norm. Okay, so what do we want to do? We want to find another matrix which rank is smaller than the rank of A, but this matrix in some sense is closest to the matrix A. In what sense? With respect to the Frobenius norm. Okay, so the idea is actually similar to this square solution, right? Remember that? When finding this square solution, assume this plane is a column space of a matrix. Then we want to find some vector that is in the column space of A, but is close to the vector B. Remember that? AX equals to B. And the so-called least square solution, AX hat, is actually this vector, AX hat. But now, we put our focus on matrix. We want to approximate this matrix A by another matrix of rank K that is closest to the matrix A, but with respect to the Frobenius norm. Okay, so the idea is quite interesting. Let M be the set of all n by n matrices of rank K, because we may have infinite numbers of choices of the n by n matrix. They are all of rank K. It can be shown that there is a matrix X in the set such that the distance between A and X, written like the Frobenius norm of A minus X, which is the minimum of all possible Frobenius norm of the distance. So we always can find a matrix X that has the minimum Frobenius distance to the matrix A. Just like this square solution, we can find a unique this square solution such that AS hat is closest to the vector B, right? Okay, but in the textbook, we will not show the proof of this property because this is beyond the scope of this book. Okay, to prove this is not an easy way. We will not show the proof, but we will show how such a matrix X can be derived from the SVD of A. Okay, so before we introduce how to calculate the matrix X, we first introduce the Frobenius norm, because actually the Frobenius norm was introduced in previous sections in this textbook, but we skip it. Okay, so what is the Frobenius norm? For a vector space R including all the n by n matrices real number n by n matrix, the Frobenius norm of a matrix A in this vector space is defined as the inner product between the matrix A and the matrix A. So what is an inner product between matrices? Actually, we just calculate, we just sum over all the value inside the matrix Aij square, and then take the square root. So for example, if we have a matrix like 1, 2, 3, 4, then the Frobenius norm of the matrix A is 1 square plus 2 square plus 3 square plus 4 square, and then we take the square root. This is the so-called Frobenius norm. And you can imagine, for a matrix, the Frobenius norm is actually similar to the Euclidean norm of a vector. If we view this matrix as a vector 1, 2, 3, 4, if we view it as a long column vector 1, 2, 3, 4, how can we calculate the Euclidean norm of this vector? How to do it? Basically, we just check the x transpose x square, right? So the Euclidean norm, or the L2 norm of this vector, is 1 square plus 2 square plus 3 square plus 4 square, and take the square root. So you can view the Frobenius norm of a matrix. It's just like the L2 norm of a vector. Okay, we just can view it as a long vector. Okay, so let's first introduce the lemma 6.5.2. If A is an n by n matrix and Q is an n by n orthogonal matrix, then actually we introduced a similar theorem before. For example, a vector Q, a vector X, if we pre-multiply this vector X with Q, with an orthogonal matrix Q, then we take the norm. Actually, the norm of Qx is equal to the norm of X. Remember that? But now we are talking about a matrix. So in matrix, we take the Frobenius norm. Okay. So how can we prove that? The QA, we take the square of the Frobenius norm of QA, and we can separate the matrix A into A1, A2 to AN, where AI is the ith column vector of the matrix A. So we can rewrite it as QA1, QA2 to QAN, and we want to take the Frobenius norm of it. And if we separately view QA1, actually QA1 is a vector. QA2 is also a vector. So in fact, just like what we say here, this value is equal to this value, right? These two are equal. So this Frobenius norm is equal to, we calculate the L2 norm of each vector QAI and sum together, right? And according to, because Q is an orthogonal matrix, so the norm of QAI is equal to the norm of AI, right? So it can be rewrite like this. And what is this? This is actually the Frobenius norm of the matrix A. So we have proved that the Frobenius norm of QA is equal to the Frobenius norm of A. So you can view this as the matrix version corresponding to this property, right? Okay. So now, if A has singular value decomposition, then the Frobenius norm of A is equal to the Frobenius norm of U sigma V transpose, right? And because U is an orthogonal matrix, so according to the lemma 6.5.2, we know this Frobenius norm is equal to this Frobenius norm because U is an orthogonal matrix. Okay? And now, the Frobenius norm of this matrix can be rewritten as the Frobenius norm of this matrix transpose, right? Because we can do transportation and the corresponding Frobenius norm does not change. Okay, so it becomes V sigma transpose, the Frobenius norm of the V sigma transpose. And again, because V is orthogonal, so the Frobenius norm of V is sigma transpose is equal to the Frobenius norm of sigma transpose, right? So finally, we know the Frobenius norm of A is equal to the Frobenius norm of sigma transpose. And because sigma is a diagonal matrix, okay? And actually only the value at the diagonal are non-zero. So the Frobenius norm of sigma is equal to sigma 1 squared plus sigma 2 squared to sigma n squared, and then take the square root. So this is an important conclusion. The Frobenius norm of the matrix A is equal to the square root of the sum of singular value. The square root of the square of the sum of singular value. This is called the Frobenius norm of this matrix. Okay? Right? So this is very interesting. So now, from theory 6.5.3, that A, we can do the SVD, which is an n by n matrix, and the M is the set of all n by n matrices of rank K, where K is between 0 and R, rank of A. Okay. If X is a matrix satisfying this formula, this equation, then what is the distance between A and X? So the Frobenius norm of A minus X represent the distance. You can see that you can imagine it's the distance between A and X. Okay, and according to the previous description, we know the Frobenius norm of A minus X is equal to the sigma K plus 1 square plus sigma K plus 2 square and so on. Okay, why? In particular, we would say why the distance between A and X, the Frobenius norm of A minus S, why is it equal to this value? Why? Okay, now if we let A prime as U sigma prime V transpose, okay, if we let A prime as this value, where sigma prime is equal to sigma 1, sigma 2 to sigma k at the diagonal, and all the off diagonal entries are 0. So it actually it can be written like sigma k 0, 0, 0. Okay. So if we minus if we calculate the A minus A prime and then take the Frobenius norm, it becomes this value, which is the minimum of the Frobenius norm of all possible A minus S. Okay, so this is the description of this theory 6.5.3. Okay, let me explain this in Chinese again. 好，这边有一点点小复杂。首先，我们之所以要学 SVD， 其实最终目的其实是要导出这个，好，我们要找到一个 rank 介于0到 R 之间的另外的一个矩阵，它呢能够近似于矩阵 A。好，那我们一定可以找得到一个矩阵 X， 在 Frobenius norm 的这个观点之下，它呢是属于 rank K， 而且呢是最接近矩阵 A 的，这样。好，那这个证明呢，我们在这本书里面根本没有提供，因为它已经超出我们这本书的范围了。好，那 Frobenius norm 你就把它想象成是矩阵版本的 L2 norm 的意思。好，那这里就提到说呢，你一个矩阵乘上一个 orthogonal matrix 取 Frobenius norm， 它的答案其实等同于我原本这个矩阵的 Frobenius norm。那我们这里也证明了，其实一个矩阵的 Frobenius norm 其实就等于是它的 singular value 取平方加起来开根号，就相当于是我把我的 singular value 形成一个向量，然后自己跟自己做内积取 norm， 意思是一样的。好了，那比较复杂的是这个定理 6.5.3 这个定理的说明，光这个定理的说明啊，就写了一整页。这只是说明哦，这还没有开始证明哦。好，他说呢，如果一个矩阵 X 它是 rank 等于 K， 好 ，rank 等于 K， 那么在 rank 等于 K 里面，这个子空间，这个集合里面有很多的矩阵嘛，其中最靠近 X 的这个矩阵，它跟 X 之间的 Frobenius norm， 或者是以前我们是讲，如果是向量，我们就讲说向量，我们就讲说这是距离啦，好，你就把它想象成距离。最靠近 A 的这个矩阵 X 跟 A 之间的距离，这个距离呀，就等于谁呢？等于是从第 k 加1一直到第 n 个 singular value 的平方加起来开根号的意思。好 ，OK， 好，那如果说有一个矩阵 A prime， 它的 SVD 可以写成这个样子。好，那其实 A 跟 A prime 的距离其实也是等于这个。OK， 好，那这个 A prime 的 rank 看起来就应该是 K， 这样。好，那所以总而言之，它这个定理主要要告诉我们事情其实是这样：这个 A 是 rank 是 R 哦，X 的 rank 是 K 哦， 一个认可为 k 的矩阵最靠近 rank 为 r 的这个矩阵 A 的最近的距离最小会是多少呢？最小就会是从第 k 加1到第 n 个 singular value 加起来，取平方加起来开根号。好，这个叫做定理 6.5.3。OK， 那你如果去翻课本，这个证明呢，漏等啊，非常的长，所以说呢，我们在投影片里面我们就不讲了。好，那个有兴趣的话呢，自己去仔细的去这个参悟一下，好，敬仰一下。OK， 那我们这里呢，只是要告诉大家这个结论。好，一个 rank 为 k 的矩阵跟一个 rank 为 r 的矩阵，它们的距离最小就是从 k 加1这个 singular value 到第 n 个 singular value， 取平方加起来开根号，这样。那很显然的，当我们在找寻这些矩阵 x 的过程当中，我们一定是想要找距离最小的嘛，所以这里就出现了它的这个，其实慢慢的，你就可以感觉得到，我们就是尽可能的取出比较小的那些 singular value， 让它加起来开根号会最小嘛。Okay, so we skip the proof of this theorem. This only for this theorem. This theorem 6.5.3 is a little bit complicated. Okay, the proof is especially complicated. So please read the textbook if you are interested. Okay, so now if A has singular value decomposition U sigma V transpose, then we can think of A as a product of U sigma times V transpose. Okay, right. If we partition U sigma into columns and the V transpose into rows, then for U sigma, this is U1, U2 to UN, this is all the sigma, and we can write it down as sigma 1, U1, sigma 2, U2. So we divided it into a column vector here. We can represent A as an outer product expansion. So U sigma can be written like this, V transpose can be written like this. So if we calculate this, we can rewrite it as sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose and so on. So this is looking like an outer product expansion. Outer product expansion, because this is a column vector U1 multiplied with V1 transpose. So this is an outer product. So now, for if A is of rank n, why do we say it's of rank n? I don't like n. Rank n. Okay. If A is of rank n, then A prime can be written as U sigma V transpose. What is A prime? Let's go back to here. Okay, here A prime is just using the first n singular value. N singular value. So this is why I don't like n, because in previous slides we use r, but here it use n. Okay, but anyway, A prime is equal to U sigma V transpose, where here is 0, 0, 0. Yeah. So A prime is equal to sigma 1 U1 V1 transpose to sigma n minus 1 U minus n minus 1 V n minus 1 transpose. The A prime will be of the matrix of rank n minus 1 that is closest to A with respect to the Frobenius norm. Okay. So similarly, we can reduce. Why do we say this A prime is closest to the matrix A with respect to the Frobenius norm? Why? Because remember that the distance between A and A prime is the sum of the square of the last singular value. So how can we set up the matrix A prime? We just need to put all the smallest singular value at the right button side, so that the sum of the smallest singular value could be minimized. We can truncate, for example, we can truncate sigma n into 0. And again, we can truncate sigma n minus 1 into 0 again. And then we can get A double prime. So it becomes sigma 1 u1 v1 transpose to sigma n minus 2 u n minus 2 and so on. This would be of the rank n minus 2, but it is closest to the matrix A in the case of rank n minus 2. So in particular, if A is a non-singular n by n matrix, then A prime is singular. And the distance between A and A prime is the smallest singular value. So sigma n may be taken as the measure. This is the final important conclusion. Sigma n would be taken as the measure of how close a matrix to be singular. Okay? This is a special case. If A is non-singular n by n matrix, and A prime is singular, remember that the A prime is of the rank, of smaller rank, which is singular. Then the smallest singular value can be taken as the measure of how close a matrix is to being singular. OK， 好，这部分呢用中文再解释一次，这部分的确是很抽象。我们刚刚讲定理653，好，那我现在呢这边是讲说，我做了 SVD 之后，我们可以把一个 SVD 视为是一个 outer 外基的展开 outer product expansion。好，那我们又讲说呢，今天如果 A 它的 rank 等于 n， 好，我现在如果要造一个矩阵，它的 rank 是 n 减1，好，然后它又能够跟 A 这个矩阵越接近的话，距离 Frobenius norm 的距离越接近的话，那这个 A prime 应该长什么样子呢？这个 A prime 呢就应该是，我就把第 n 个 singular value 把它 truncate 变成0。好，那这样子造出来的矩阵 A prime 呢，就会是 rank 是 n 减1，而且是最接近 A 的那个矩阵。为什么呢？因为 A 跟 A prime 中间的距离，就是从你最底端最编号最大的那个 singular value 开始加总加起嘛，对不对？好，那我今天 A prime 跟 A 差在哪里呢？只差在最后面的这个 sigma n 的这个 singular value， 这中间有一点误差嘛，因为本来呢，对于 A 来讲，它其实是有一个，你这里有一个这个 un sigma n 嘛，它有这一项嘛。那你现在对于 A prime 来讲 ，A prime 等于谁 ？sigma one u one v one transpose 一直加到 sigma n 减一 u n 减一跟 v n 减一 transpose， 所以呢 ，A prime 跟 A 的误差其实就在这一项，在这一项，就相当于我在造 A prime 的时候啦，我把 sigma n 呢闯 k 变成0的意思，所以它们的误差就是这一项。那我当然我希望误差越小越好嘛。好，所以呢，我如果要在一个 rank n 减1的这个集合里面找一个矩阵跟 A 最接近的，那就是它了。同理，如果你要去找一个在 rank n 减2这个集合里面跟 A 最接近的，那就是它了。那它就是把 sigma n 想办法闯 k 成0 ，sigma n 减1也闯 k 成0，因此它加起来长这样嘛。那后面呢 ，sigma n 跟 sigma n 减1带来的就是你的误差，你希望这个误差越小越好，对不对？好，那如果今天 A 是一个 non-singular 的 matrix， 它有什么应用？这其中一个应用。A 如果是一个 non-singular 的 matrix，n by n 的 matrix，A prime 呢是你拿掉，比如说你拿掉一个 singular value 之后，它变成 singular， 这个矩阵变成 singular 了。那么到底你这个矩阵 A 它是一个 non-singular value、non-singular 的 matrix， 它距离 singular 有多么近呢？这个评估方式就是用这个 sigma n， 就是这个可逆矩阵跟它的不可逆最接近的不可逆的版本中间差多么近呢？就是用这个 sigma n 来衡量，来衡量。OK， 好，所以这一段的说明呢都有点妙哈。So let's go to example number 3. Let n be an n by n upper triangular matrix, whose diagonal elements are all ones and whose entries above the main diagonal is all -1. So it is looking like this. Okay, so we know that the determinant of A is equal to the determinant of A inverse is equal to 1. And all the eigenvalues of A are 1. Okay, this can be easily verified. However, we will show that if n is large, for example, if this matrix A is a very large upper triangular matrix, if the n is large, very large, then A is close to being singular. So we know in this n by n upper triangular matrix, for example, this matrix is 10 by 10, for example. For this 10 by 10 matrix, because the determinant of A is not equal to 0, so this is a non-singular matrix. It's invertible, right? However, we show that if n is very large, for example, it's 10,000 by 10,000. If A is a 10,000 by 10,000 matrix, now let the matrix B be this matrix, which is also a 10,000 by 10,000 matrix. The matrix B is almost the same as the matrix A, but with the value at this position, which is -1 divided by 2 raised to the power n minus 2, for example. So because n is very large, so this value can be very, very small, right? Okay, so the matrix B, actually the matrix B is singular because Bs equals to 0 has non-trivial solution. This is the trivial solution, non-trivial solution. Okay, So originally the matrix A is non-singular, but the matrix B is singular. But matrix A and B is very similar. The Frobenius norm between them is just 1 divided by 2 raised to the power n minus 2. The distance between them is very small because n is very large. Okay. So from the theory 6.5.3, the singular value, the nth singular value, is the minimum of the Frobenius norm, which is smaller or equal to this value. So if n is 100, then the sigma n is smaller than this value. So actually, the matrix A is very close to singular. So this is what we want to say, that theoretically, the matrix A is non-singular. It's non-singular because its determinant is not equal to 1. However, practically, this matrix is very, very similar to singular. Very close to singular. Okay? The matrix A is very close to singular. Okay. So now, let me show you some example. In real application, we will introduce 2 applications. Okay. The application number 1 is called the numerical rank. In most practical applications, matrix computation are carried out by computers using finite precision arithmetic. If the computation involves a non-singular matrix that is very close to being singular, just like the matrix A we mentioned before, then the matrix will behave computationally exactly like a singular matrix. Although theoretically, in linear algebra, we like non-singular matrix. We like invertible matrix, right? So even if this matrix A is non-singular theoretically, but in real calculation, when we use a computer to calculate many times, the matrix will behave computationally like a singular matrix. So in this case, computed solution of the linear system may have no digits of accuracy. Okay, the solution may be not useful. So the singular values provide a way of measuring how close a matrix is to matrix of lower rank. So in real engineering applications, we may need to do this process to measure if the solution we obtain is reliable. Okay, so the numerical rank of an n by n matrix is the numbers of singular values of the matrix that are greater than this value, sigma 1 times maxima mn times epsilon, where sigma 1 is the largest singular value of A, and the epsilon is the machine epsilon. Okay. Yeah. So what is the numerical rank? We can see, we can view that numerical rank is just like the, you can see it's you can view it as the main characteristic. The most important information can be embedded into a lower rank matrix of the numerical rank, and which is larger than sigma 1 times maxima mn times epsilon. This value can be dynamic according to how we set the epsilon. Okay, so let's see some example. Suppose A is a 5 by 5 matrix with singular value for 1. This should be 10 raised to the power negative 12. Okay, sigma 4 and sigma 5. Okay, so we can see that basically the first two singular values are much larger than others, right? And suppose the machine epsilon, we manually define it as 5 times this value. To determine the numerical rank, we compare the singular value to this value. Okay, and since the 3 of the singular values are greater than this value, then the matrix has numerical rank 3. So we said the numerical rank of this matrix is 3. 好，这边在干嘛呢？就是说，实际的应用当中，如果一个矩阵，它虽然是理论上是可逆矩阵，但是它的数值其实已经很接近是 singular matrix 的。好，那我们在实际应用上呢，会产生一些数值的问题，我们算出来的解可能没有什么实际的用途，可能并不符合实际的需求。好，那所以说呢，我们有时候会去评估我们在这个线性系统里面，我们这个矩阵的 numerical rank 是多少。好，那这个 numerical rank 是多少，会根据比如说你的应用而定，或者你这台机器你可以容忍的，比如说误差啦什么等等的，去设定你这个 epsilon。那这个 sigma 1乘上m 跟 n 里面比较大的那个，再乘上这个 epsilon， 这个算是一个在这个也不是固定不变的一个定义啦，就是说你在不同应用里面，这个可能会有点变。好，假设今天我们是设定成这样子，那么假设今天呢，你所面对的问题矩阵 A singular value 刚好是4、1、10的负12次方、10的负14次方、10的负15次方，而你的 machine epsilon 设定成这样子，那么我们就说，其实啊，你这套系统距离你的 numerical rank 是3，好，那距离 singular 可能就是其实非常的接近，因为你就是 sigma 4跟 sigma 5加起来，其实非常非常的小。好，那你可以去评估说，这样子算出来的解答是否符合你真正的这个系统的需求。Okay? Another application is about digital image processing. Because we know that an image can be digitized into a rectangular array. That's called pixels. So the digital image can be stored using an n by n matrix A. So generally, the matrix A will have many small singular values. So A can be approximated by a matrix of much lower rank. So here we can write the matrix A as an outer product expansion, and the closed matrix of the rank K is obtained by truncating the sum after the first K turns. Okay, so we just pick the first K largest singular values. Okay, so in this way we can reconstruct the matrix A based on this. We can approximate the matrix A by AK. So in digital images, this is the original image. We can store it as a matrix. If we approximate this original matrix A by A5, that means we just use the 5 largest singular value to approximate matrix A, then the image is looking like this. If we approximate with 15 singular value, the approximation will be looking like this. If we approximate based on 30 singular values, then approximation is looking like this. So we can see that with more singular value, we can do better approximation. And according to this effect, actually, we can develop many technology. For example, data compression, image compression, right? Because the approximation is looking very similar to the original image. So in this way, we can largely reduce the numbers of bits we need to store this digital image, right? 好，所以这边呢，我们可以把一张影像视为是一个矩阵，而这个矩阵呢，通常会有很多很小的 singular value。那既然这些东西很小，我把这些很小的 singular value 都忽略不计，令它等于0。那其实我可以用保留下来的那些 singular value 的值啊，我去做这个 outer product expansion， 我用 AK 来近似原本的 A， 而这里就秀出一些例子。好，你如果用30个 singular value 来近似原本的 A， 其实已经蛮接近的。而这样的好处是什么？这样的好处是说，我只需要去记录前30大 singular value 以及对应的那些right singular vector 跟 left singular vector， 我就可以去重建这个原本的影像。那这样子呢，我可以大幅的减少我需要储存这一张影像的资讯所需的这个 data size。那这个就是资料压缩啦。这个就叫做资料压缩。我用比较少的资料量来表达一样的资讯，那这个就是资料压缩了。资料压缩的其中一种做法。OK， 好，那所以呢，这边呢，我们就是刚好今天3个小时，我们把 Section 6.5讲完了。这个部分的确是蛮困难的啊，真的是要耐着性子、耐心的去仔细的看。好。